Good afternoon, everyone. I'm Junyong from Hyeonseong University. Today, I will introduce the Blind-QEM, a privacy-preserving framework for quantum error mitigation in the cloud quantum computing. The core question is simple. Can a user receive the useful error mitigation from the external service provider while keeping the circuit topology private? Our answer is to combine the zero knowledge proof and the QPU-signed execution receipts, so the service can verify the policy compliance and the result integrity without seeing the full circuit. Quantum error mitigation is becoming a service in the cloud. However, this creates a conflict. One side, efficient mitigation often benefits from knowing the circuit structure. On the other side, the circuit topology may reveal the user algorithm and therefore their intellectual property. The service provider also has something to protect. Its calibration data, noise model, and mitigation strategy. Blind-QEM addresses this. The goal is not to hide the computation from the QPU. Instead, the goal is to let an external mitigation service verify that the request is valid, bind the result to the real QPU execution, and then perform a blind compatible mitigation using only the aggregated information. This figure shows the overall framework workflow. The user owns the raw circuit, kept it local. First, the user commits the canonical encoding of the circuit and probe and zero knowledge that is satisfied the service policy. Then the circuit is executed on the QPU, which returns the noisy result together with the signed execution receipt. Finally, the service provider receives only the metadata, a zero knowledge proof, and aggregation with sources statistic. In this way, the provider can decide whether the request is valid and can perform mitigation, but it does not learn the detailed gate order or intellectual topology. The protocol has three main checks. First is the verifying filtering. User commit to the circuit, provide the hidden circuit, certify the basic policy. For example, supported gate, shot limit, or resources budget. Second is receipt-based result blinding. The QPU signed the execution receipt, and the user provides that the disclosed resources vector was extracted from the same commit circuit. This prevents the fabricated result and misreported resources. Third is calibrated-based blind mitigation. Since the service does not know the full topology, Blind-QEM focuses on the mitigation methods that can work from the aggregate statistics such as global fidelity estimation and the tensor product without error mitigation. To summarize, Blind-QEM adds a trust layer to the quantum error mitigation of the service. It protects the user by hiding the circuit topology, protect the provider by enforcing the service policies, to protect the marketplace by binding result to the QPU execution. For the future work, we plan to implement the Jeihee circuit efficiently and expand the set of blind compatible mitigation strategy. Thank you.